on, I'm going to draw a few graphs, then I'll know. So the next one in terms of shear is this value, okay? Now there's a positive, negative, we don't know yet, okay? So how do we know? Okay, so the next thing I want to do, okay, is we are going to sketch the stress field. The thing about this course, okay, when we calculate the stresses, it's not an average. I repeat again, we are able to determine, okay, the stress distribution. So what do I mean by that? Okay, this formula over here, okay, this formula over here is the only one that calculates the average, right? Because it's force divided by area. The rest, you know specific distance, you know the y distance, you know the radius, and you know the first moment of area. Don't worry about first moment of area. When we get to shearing stress, I will teach you more. These three components, these three formula over here, we are able to determine the stress distribution. Okay? We are able to determine the stress distribution. Okay. Now, what do I mean by that? Okay, what do I? So we are. The next slide I'm going to do. We are going to sketch, okay, an intelligent guess on how the stress field will distribute. Okay, so I'm going to copy this diagram. Come here. Okay, so we're going to look at the formulas now. Oh, I should not have deducted. We're going to look at the formulas now. Okay, so we know the axial force, right? We know the axial force that is inducing 2,000 pound-feet of pound force. Okay, so how does the stress field distribution look like? So what I'm going to draw now is I'm going to draw the stress field distribution. Okay, so I'm going to put this here. So we are going to sketch the axial load. Okay, so this is my normal stress, and then the next one is going to be my y value, right? And this is my sketch. Okay, this is my sketch. Okay, so this is equal to my minus px over a. So the structure is going through compression. Okay, right? So this is at this point will be the maximum radius. At this point will be my minimum radius, or my positive negative radius. Okay. Then the next one, the next stress distribution. So this is the average, right? Px over A is the average. So we assume that it's going to be a average. Okay. Now the next one we are going to plot due to bending moment. And bending moment is in mz. Okay. Then again we have our normal stress. Okay. And then we have our y. So we know that at point C is compression. So this is how the bending moment will distribute. Okay, we know that point C will be in compression, right? So this is how the stress will distribute. So we have compression, and then over here is a tension. Okay, so what you realize that over here at where 0, this is at the centroid, right? The centroid has 0 stress. Okay, further away from the centroid, your stresses are high. Then we look into our radius. Okay, we look into our torque, our shear stress, or we look at our torque due to our Tx. Okay, so now I'm going to draw shearing stress. I'm going to sketch out shearing stress. Okay, so this is the radius, right? And then this is the shear stress. And we know, right? The further, because the formula states that the shear stress is equal to TR over what? J. T and J are constant. It's only the radius that are changing. Okay. So what we get is we get a shearing stress looking like this. Okay, we get a shearing stress looking at like this. So the shearing stress is 0 at the center, or when the radius is 0, and then it goes to the maximum when the shearing where hold on, it goes to the maximum where the radius is the biggest, or the maximum radius. Okay, so this is how our shear stress look like. Okay, and which is fine. This is superb. The problem now is come to the shearing stress. So the last one is due to the shear force. If we have a shear force, and the formula is shear is equal to VQ over IT. Okay. So now we sketch this. So for this case, okay, it's good. We're going to see a parabolic response. And I'll derive to you why parabolic, okay, when we go to shear. And over here, this is where our tau max is. And all of them, okay, all the diagrams over here, you can see that this at this point over here, this is at your centroid. This point over here, this is a centroid. Now the problem is this, right? For axial force does not matter, right? Whether you are at the centroid or further away from the centroid, right? Further away from the centroid, the magnitudes are all the same, fine. The bending moment, what we are plotting is the distribution, because the formula is equal, as I mentioned, mz over izz multiplied by y, right? And we realize that what changes is y is the thing that is changing. So the further away you are from the centroid, the bigger your stresses. So you get a stress. So for bending moment, you realize that at the centroid, the normal stress is equal to 0. Now you look at the torque, somehow it's a kind of good news because the centroid has 0 stress. Further away, when the radius is bigger, you have higher shearing stress. If you were to look at the shear force, something not so good news happened. What is not so good news is this. The shear force at the centroid is where maximum shear stress will occur. Away from the centroid is where you have zero shearing stress. Okay. So again, now from here you're like, whoa, how are we going to solve this problem? Okay. Now, why I'm highlighting this? I'm highlighting that because we don't know in terms of shear which has a higher shear. Point B or point D. Normal stress, we sorted it out already. Okay, normal stress, we know it's point C because we have minus Px over here. We have minus Mz over Izz multiplied by Y. When you combine them in terms of normal stress, the magnitude is going to be the highest. How about shear? Which one? Okay. So now we're going to focus on the shear. So if we were to visualize how the torque has been applied, okay, how the torque has been applied. So I'm going to draw the shaft again. Okay. So the moment in the torque in X is going to be in this direction. Okay. So this is the torque in the X direction. Okay. So all the shear stress will go this way. These are all the shear stress. It's flowing in that direction. Right? So this is your element A, element B, element C, and this is element D. Okay. Now, in terms of your shear force, okay, I'm going to copy this circle. Okay. So we know that this is equal to your Vy, right? So this is your element A, element B, element C, and over here is your element D. Okay. So the smaller the arrow, the smaller is the magnitude. So I'm going to draw this now. Okay. The bigger the arrow, the bigger the magnitude. Don't worry about this. You will learn later on. Okay. Okay. So now, at element B, and at element D, right, is where the arrow, the shear flow arrow, this is what we call, so what I'm drawing down here is what we call Q. Later on, as I say out, this is known as your shear flow. Okay. Now, if we were to combine both of them, okay, if we were to combine the torsion and the normal stress, so I want you to focus on these elements down here. Okay, I want you to. So the yellow one is due to the torque. The blue one is due to the shear force. Now, which element will see the higher shear stress? Element B or element D? Anyone? It's 50-50, okay? You can make a guess, but you have to explain to me why. Tyler?
That would be D.
You're absolutely right. Now, why is Tyler right? Okay, the thing is, why is he right? If you look at the torque now, right? The shear stress is coming down in this direction, right? And if you look at the shear force or shear flow, it's in the same direction, yes or no? So element D, both the torque and the shear flow are in the same direction. In element B, right, the torque is generating in so-called anti-clockwise direction, but the shear flow is